so we're happy to have Sebastian Seemann, who will tell us about Vandermonde cells as positive geometries.
So, hello everyone, thank you very much for allowing me to be here and for organizing the great conference. So I want to tell you about Vandermonde cells as positive geometries. And this is a joint work in progress with my advisor, Vandermonde. So I will start in the first section to tell you what Vandermonde cells are. I'll give some motivation, where they come from, how they arise. And in the second section, I will tell you about polypols, which are special semi-algebraic subsets for Rn. Some of them are positive geometries and well understood in that setting. And then in the last section, I will talk about canonical forms of those Vandermonde cells and what works and maybe what doesn't work. Okay, so let's start by some motivation. So let's say we have a let's say we have a trace polynomial in even powers of symmetric matrices. So something like this, a trace of a squared multiplied with the trace of b to the 6th power minus trace to the a4 times trace to the b4. And we want to know, is this bigger or equal than 0? Is this non-negative for symmetric matrices of all sizes? And the answer is no. This is actually an undecidable problem, and but it becomes decidable quite quickly if we just replace the trace by the normalized trace, which also takes the size of the matrix into account. And how can one understand this problem? So the key is the geometry of those Vandermonde cells. So now let me define them. So I note by PD, P power sum polynomial. This is just a power sum polynomial. And then we define the Vandermonde map, which is a polynomial map from Rn to Rd. In the ith component, we have the ith power sum polynomial. So then from this, the ndth Vandermonde cell, denoted by pi nd, is then the image of the probability simplex. So all elements in Rn that have coordinates bigger or equal than 0, and also the coordinates add up to 1. And we map them with this Vandermonde map, with the images of ndth Vandermonde cell. And here are some images of the boundaries of those cells. And one thing I should also mention, so those are pi 3,3, or boundaries of pi 3,3, pi 4,3, and pi 5,3, but they're planar, and the reason for this is simply if we restrict the map to the probability simplex, and the first coordinate will always be 1, so we just project it out. So how does this connect to this non-negativity question? So the reason is that the non-negativity of this trace polynomial is actually equivalent to non-negativity of this polynomial, 2a1b3 minus a2b2, on the product of those Vandermonde cells. The ai and bi are the ith power sum polynomial, the respective vector. So in consequence, this means we're interested in non-negativity of polynomials on products of Vandermonde cells. And also, if we want to consider non-negativity for matrices of arbitrary size, then we need to look at Vandermonde cells where n goes to infinity. So we need to take the limit Vandermonde cell by pi d, which is just the closure of the union. Then there's our nice properties. So the boundaries and preimages are well understood. So this goes back to there's an explicit description of the preimages of the boundaries going back to 59 by Ursel. And also another thing that's really interesting about them is that they have the combinatorial type of cyclic polytopes. So this resources from last year. That's a wide span. But there's also earlier work that looked at those maps or power sum maps or their images. And so the first one I pointed out here is this work by called Recovery from Power Sums by Anna Milanova, Bernd Sturmfels, and Rosa Winter. Essentially, what they look at are fibers of this map. So maybe I can tell you one conjecture from this paper is that, so if we're given n+1 power sums of co-prime powers in n variables, then recovery is essentially unique, meaning that this power sum map is generically injected. It's an open subset where it's not one-to-one, because we can always permute coordinates. It's generically n factorial to 1. And the other one I pointed out is this work by Konka, Krappenthaler, and Watanabe, those regular sequences of symmetric polynomials. And I oversimplified by saying to look at fiber over 0. Essentially what they do is, so they look at collections of symmetric polynomials, in particular power sum polynomials, and they're interested in when do they form a regular sequence, or when is 0 the only common solution, so where we have the same number of polynomials as variables. So now let's continue with polypols. What are those objects? So they're natural generalizations of polytopes, since that polytopes are given by linear boundaries, but now we also allow nonlinear boundaries, and the semi-algebraic set they cut out. And they have various applications in numerical analysis and statistics. So this is actually where they come from. So Max Press was trying to generalize finite element methods from numerical analysis. So he tried to introduce more complicated building blocks, just cubes. And here I given a definition of one particular subclass of those polypols. And so it's not really important what exactly the subclass is, but the point about this particular subclass is that for those, computing canonical forms works essentially exactly as for polytopes. So will be a unique adjoint, as in the residual arrangement has enough points, so that there's a unique curve to correct degree. And then the canonical form will just be given as this quotient. So in particular, just read it, so what we want, so those are called regular rational planar polypols. And so we have irreducible rational boundary curves, Ci, and we have real vertices, which are contained in, so they're pairwise different. It's also important. So with real vertices contained in adjacent boundary curves, we always choose a segment on this particular boundary curve between two adjacent vertices. And we also choose a simply connected semi-algebraic subset. That's it's then supposed to be the positive part. And additionally, we require that C is non-singular on the interior of the segments. And we have transversal intersections into the IJ. So I have some pictures here from this nice paper where they were studied by Kohn, Pien, Ramstedt, Breidel, Shapiro, Sim, Sorea, and Thelen. And so here are some polypols, and the numbers below are the respective degrees of the boundary curves. The shaded region is supposed to be the positive part. And then maybe you can make it out. There are some points contained in the residual arrangement, in the singularities and the singularities of the boundary curves outside of the boundary itself. And then the theorem I mentioned just now is that regular rational planar polypole with the boundary curve cut out by square-free equation f is a positive geometry. It has a unique adjoint, and the canonical form is given as expected. And so, okay, but there are also a lot of polypols which don't fit into this specific subclass, but for which we can still write down canonical forms in the usual way. So for example, there's this one, the ampersand curve. So by now somewhat older example, where so there are the differences that we have only one boundary curve. Then here on the right, there are two quadratic boundary curves. So the reason why this is not a planar rational polypole as defined before is that single boundary curve contributes multiple parts of the boundary. Then here there's some, so here we have another example. That is actually part of the boundary is this cubic with a cusp, but in particular the singularities at the vertex. So this intersection is far from transversal. But then we also have examples like this, where there are no singularities on the boundary curves themselves, but we still have a non-transversal intersection here.
And those are all positive geometries.
Yes, those are all positive geometries, and can actually write down canonical forms. So the first, so this one actually is already in the book, positive geometries and canonical forms. Those two are given in this paper, and this one is one example that you might write up in this current work in progress. So I said the boundaries are well understood. So how do they look? So for pi n3, the boundary segments are the curves b2 to bn, where bk is this given by this polynomial, and particular, so b2 is a line, and all the other ones are cubics with a cusp. So this also means that if we enlarge n, we still keep the old boundary curves. So we're just adding new ones. And so here are some examples. So this is pi 3, where we have this one line as a boundary curve. And then in blue, the cubic with a cusp. There's a non-transversal intersection here at 1, 1. And then what happens if we go to pi 4,3? So we add this additional orange cubic with a cusp, and basically build up this or add on to this small sliver here. And it goes on like that. Okay, so now is this a positive geometry? So there's a straight problem. So this interior of the cubic boundary segment is not smooth. So this actually contains a singular point within the interior. And it's part of the definition of positive geometry, actually, that the interiors are manifolds with an orientation. So this does not fit. So I think we could say now we're done. It's not a positive geometry. But maybe let's see if we can still write something down that resembles a canonical form and maybe satisfies the other properties. But you saw the equations are somewhat large, so let's simplify and also remove the non-transversal intersection for now. So let's just consider this simple cubic. Y squared is x cubed, and we enclose a semi-algebraic subset with the line x equals 1. And then to avoid the problem of having this singular point in the interior, we also subdivide this thing with the line given by y equals 0. And now we're actually back in the case from before that. So look here, so here we had a cubic with a cusp, and the cusp was part of the boundary. So this should work. And it does. So then only considering residues along the two boundary lines, we get enough conditions to obtain two canonical forms. And adding them up, we obtain this form. So now let's look what happens if we compute the residue along the cubic, how we usually do it for polytopes. So we write our omega. So I wrote this out explicitly because we haven't seen so much of this in the conference, so maybe it's not so bad. So the recipe goes as follows. So we write our form as d of our boundary curve divided by the boundary curve wedged with some degree 1 lower form, giving this, and then the residue is given exactly by this form beta. So the residue along this cubic, so we obtain something 2 divided by 3x times x minus 1 dy restricted to this curve y squared minus x cubed. So it doesn't look so bad right now, but if we actually use this equation to write the form purely in terms of y or x, we get some cube roots. But let's not do this and just use the standard parameterization of this cubic with the cusp we know of. So we can parameterize the cubic by t squared t, and then evaluating this, we get exactly what we would want for a line segment. So it's, and I guess you could say that this parameterization is like a desingularization, it's removing the singularities. So this is what we would expect on this line segment of length 2. So it seems to work, or provide something interesting. Yeah, and then I wrote a small sentence about non-transversal intersections. This is actually also in this particular planar case not so difficult. So we can approximate. We just see that it seems like the right condition is that a joint curve also has to pass through its non-transversal intersection with a corresponding multiplicity to kill the remaining residues. Okay, so now to finish off, let's talk about the limit. So what's happening with the limit? And the problem is that this is not even semi-algebraic. So and why? So we see. So I explained if we increase n, we add an additional cubic, and what also happens is we get a corner or a vertex for every cubic we add. So in total, in the limit, there will be infinitely many singularities on this boundary. So this thing is not semi-algebraic anymore. So there's no chance, right? How would this canonical form even look? In the denominator, we would have infinitely many equations for all those boundary curves. Then this is not a meromorphic form. Yeah, however, one approach that could still work, that gives at least a function, is emulating this volume description that we've seen for polytopes. That's also been tried. That we've heard a lot about that. It's a big quest to enable us to use such a volume description for the Amplituhedra, to find this dual Amplituhedra. Yeah, and here this works as well. So pi d, it's a bounded subset of Rn, so it has a finite volume. And so if we move it so that the zero is in the interior, then the dual is actually also a bounded polytope with finite volume. We can take this as the value. Yeah, however, we still have this problem, right? So this function has infinitely many poles. So whenever we move to any boundary curve, we have a pole, so it's not so clear how this is supposed to look. Thank you.